Greetings, this is Mr. T. This video is commentary for Packet 13, Intermolecular Forces and Solution Chemistry, Part 1. In this commentary, we're going to get into the concepts of intermolecular forces. You'll learn about the different types and use those to predict solubility of pure substances mixed together. So here's the outline for it. In addition, the back of the outline contains a special flow chart which walks you through the steps of how to predict what type of intermolecular force for a specific molecule. So let's go ahead and get started. Intermolecular forces refer to attractive forces between the molecules. So for example, if I were to have H2O, water, it's the cohesive forces between the molecules. We've studied the intramolecular forces, and that means the forces inside, such as covalent bonds, ionic bonds, but now we're looking at between. This will allow us to figure out such scenarios as will one substance dissolve into another, like salt into water. So let's start with the like dissolves like rule. The purpose of the intermolecular forces is to figure out whether each substance will be polar or nonpolar. So once we figure out whether it's going to be polar or nonpolar, we follow the like dissolves like rule, where polar and polar mix together perfectly, nonpolar and nonpolar mix together perfectly, and then polar and nonpolar, they do not mix, or they mix poorly. Dissolve, mix perfectly, and soluble, these are all the same thing. So you'll notice that I use those words interchangeably. Here's an example of a nonpolar substance, and this is oil. And then water is going to be polar, which you learned about a while back. And going by the like dissolves like rule, polar and nonpolar do not mix, so they create separate layers. So here are examples of different substances. One is polar, the other one's nonpolar, and therefore they do not mix. And using the intermolecular force rules, we're able to identify which substance is polar or nonpolar and then predict whether they are going to be soluble or insoluble even before actually doing the experiment. Slide 4 is super important. You need to memorize this slide inside and out. Memorize the 4 types of intermolecular forces talked about in this class: ionic, hydrogen bond, dipole-dipole, and London. Memorize that 3 of the intermolecular forces are categorized as polar, whereas the other force, London forces, is going to be nonpolar. Now, for this class, these are the terms that we're going to use, but there are other terms that mean the same thing. So instead of London forces, there's another term called dispersion forces. Also, there's another term which is an umbrella term for dipole-dipole and London forces called van der Waals forces. But for this class, I'm going to use these 4 exclusively. Notice in this slide we've also ranked. That spells rank, believe it or not. There we go. We've ranked from strongest to weakest intermolecular forces. So ionic forces, that's the queen, the strongest, followed by hydrogen bond, then dipole-dipole, and London. Now, polar means opposite charges. And it turns out that this intermolecular forces has to do with opposite charge attraction. So polarity is the strength of this opposite charge attraction. So ionic forces is the strongest, and then London forces is going to be the weakest. So memorize that. There's also some other trends that we're going to be getting into. Boiling point and solubility in water. There is a direct relationship between polarity and boiling point. So the higher the boiling point, then the higher the polarity, and vice versa. So it's a direct relationship. So automatically, if I wanted to rank by boiling point two molecules, I can simply look at the intermolecular force and then make a guesstimate of which one has a higher boiling point. So for example, if I were to sit there and have ammonium sulfate, it's supposed to be a 2 there, and I were to have methane gas, ammonium sulfate is ionic forces, and then methane gas is London forces. Ionic beats London, so ionic is higher. Consequently, the boiling point is going to be higher for ammonium sulfate than London. Now the same thing occurs for melting point. There's the same ranking scheme, but we tend to use boiling point. As a reminder, and I'm using sodium chloride as my example, boiling point refers to the temperature at which the substance turns into a gas. So here are my sodium chloride particles, and if we apply a high enough temperature, not only would they melt, but at a specific temperature, then they would all separate into floating gas particles. In short, however, the stronger the intermolecular force, the stronger the cohesiveness between those particles, so therefore you need a much higher boiling point. But that's as much as we talk about the concept of boiling point. Then there's solubility, how well a substance dissolves in water. So the more polar the molecule or particle is, then the more soluble it is in water. So it's a direct relationship. So therefore, sodium chloride is much more soluble in water than hydrogen gas. So let's go into each of the 4 types of intermolecular forces. We'll start with ionic forces. In short, the whole reason intermolecular forces occur is due to opposite charge attraction. So every time I talk about the concept of an intermolecular force, just keep in mind that there's some sort of opposite charge attraction that's occurring. So for example, if I have a sodium chloride, before we said that the positive and negative would cancel each other out. Well, I lied. There is a residual partial positive, we use that delta symbol, and partial negative that's left over. So therefore, the attraction between this particle and another particle is due to opposite charge attraction. Now, you know you're dealing with ionic forces if you're dealing with an ionic compound. So that one's pretty straightforward. So if you see a metal and a non-metal, then automatically it's going to be ionic forces. In addition, if you were to see any type of polyatomic ion present, such as ammonium chloride, we know that that's a polyatomic ion, then automatically it's going to be ionic. And of course, if there's any molecule that has a visible negative charge, then automatically it's going to be ionic. So that's a molecule called F oxide. I know it looks kind of weird. It's got that weird dash to it. You get into that when you get into organic, and that's a long time from now. Now we're going to get into dipole-dipole. Let's go ahead and get into the name first of dipole-dipole. Here is hydrogen chloride. Based on the electronegativity rules, chloride is more electronegative than hydrogen because it's closer to fluorine. And so that's a positive. Now, and then we talked about there being a dipole that's present. Now, the intermolecular force is due to dipole-dipole attraction. So for example, if I were to sit there and draw another hydrogen chloride, and I'll go ahead and I'll do this in using a black marker. There's a partial positive, partial negative. There's a dipole going this way. And then they're going to be attracted to each other due to opposite charge attraction. So the yellow indicates the attraction. The positive, let me say it again. The partial negative on the chloride is going to be attracted to the partial positive on the hydrogen on the other molecule. So therefore, we consider this a dipole-dipole forces. The name is kind of lame. One of the molecules has an overall dipole. The other molecule has an overall dipole. Ergo, we call this dipole-dipole. Shocker, I know. Now, in order to figure out whether there's dipole-dipole forces, you need to go ahead and sketch the Lewis structures for these. And then you need to go ahead and put in the dipoles to figure out if there is an overall dipole. So this heavily draws upon the ionic and covalent compounds part 2. So make sure to review the shape table, the concept of overall dipoles, the structures. You need to have all that down for this stuff. So as you're learning, all new concepts are built upon old concepts. Now, dipole-dipole forces, even though it's not stated here, it's in the polar category, so these are obviously polar molecules. Now we're going to get into hydrogen bonds in just a second, but I want to skip this and then jump down to this example right here. Here's dipole-dipole again. And then here's chlorine monofluoride. I'll go ahead and I'll use my red pen to draw in the dipole. There's a dipole right there. Here's another dipole. And again, they're attracted to each other due to partial opposite charge attraction. And they get the name dipole-dipole. Get it? Get it? Now let's go into nonpolar molecules. Nonpolar molecules have no overall dipole. So for example, carbon dioxide, shown in this slide 10 right here. Oxygen's more electronegative than carbon. So partial negative, partial positive on the carbon, and then the other oxygen is more electronegative than the carbon. And that's again due to the trend where the closer you are to fluorine, then the more electronegative you are. Oxygen's closer to fluorine than carbon is. Now, because there is a equal pole in opposite directions, then they cancel each other out, and there is no overall dipole. If we go over here, this molecule is also considered nonpolar because it has no overall dipole. Having drawn the Lewis structure, although it is missing the lone pairs on each of these, so this is technically not an accurate Lewis structure. Chlorine's more electronegative than carbon is. Why? Because chlorine is closer to fluorine. Now, I go and I put in the individual dipoles, showing the direction of the movement from to the partial negative, and you'll notice that they overall cancel out. The left and right dipoles cancel out, the up and down ones cancel out. So again, there is no overall dipole. So in general, when you're dealing with a nonpolar molecule that has that no overall dipole, it's automatically classified as London forces. London forces. So I'm just going to go back a second. We talked about ionic forces, we talked about dipole-dipole forces, and we talked about London forces. And it's not written here, but if I were to sit there and have my CH4 like this, now you know that it's going to be nonpolar and therefore London forces. And again, London forces is the only one for this class that's classified as nonpolar. And you know that you have to sit there and sketch it all out using the proper Lewis structure. Put in the dipoles. In this case, this is the dipoles are going in because carbon's more electronegative than hydrogen. They all cancel out, so there is no overall dipole, and therefore London. Now, all the dipoles cancel out, but there is still opposite charge attraction that is occurring. So yes, there's going to be a slight partial negative, partial positive, partial negative, partial positive that occurs between the molecules. So how is that possible if the dipoles cancel out? So let's go from slide 10 to slide 11. So this is what we believe happens. Whenever you don't have any naturally occurring permanent overall dipoles, then nature actually creates temporary dipoles. So for example, let's take a look at hydrogen gas and hydrogen gas. There is no overall dipole in each of these. It's homodiatomic. They have equal strength, so it's no overall dipole. However, it turns out that, and this is what we found to be true, even though it seems far-fetched, there's a lot of ambient energy in the room or in the area that the molecules are in the form of heat, in the form of light, and then we'll just focus on light for this class. So this radiant energy is going to come along, and it's going to zap the electrons in the covalent bonds. And it essentially, the energy acts as a Red Bull for the electron, or sugar to your 6-year-old. And what happens is it makes the electrons very active, and then they start rocking back and forth, and it creates an instantaneous dipole, where maybe all of a sudden the electrons are hanging out on one side. And in a normally neutral molecule, we now have a temporary partial negative and partial positive. So this is called an instantaneous dipole. Now, if we use the children analogy, and the electrons are hanging out on one side because they're all supercharged from all the sugar they had, one side is partial positive, and just as in real life, some children can have a bad influence on another child. So for example, if a person likes to eat candy, then maybe they will convince another child that only eats broccoli, hey, try out this candy, and all of a sudden now they're addicted to candy. Yeah. So the same thing occurs with molecules. The partial positive, for example, on this hydrogen molecule is going to go ahead and influence the molecule to the right, and if this is partial positive, it'll cause the other molecule to be partial negative. So that partial positive will cause the electrons inside to go ahead and bunch up to one side, and then the other hydrogen will be a partial positive. So we call this an induced dipole. So we went from instantaneous dipole, which you need to know in this section right here, and then we went to induced dipole, which is right here. Now that they both have these temporary instantaneous and induced dipoles, then opposite charges will attract. Now, just like a real bag of candy or a Red Bull, eventually the energy depletes and the electrons go back to normal and they become neutral again. So this instantaneous and induced dipole are temporary dipoles. They're temporary. So what happens after this? Well, when they go back to normal again, well, more energy will come along and recharge the electrons, and the whole process repeats itself. And because there's a ton of energy that's always around us, then these electrons are constantly always being recharged, just as there's a ton of candy to recharge your 6-year-old. So please know these steps of how to generate these temporary dipoles in London forces. You could be tested on this. Now, in short, there's some little helpful hints. If you're dealing with any diatomic molecules, and by the way, they have to be the same atom, this is referred to homodiatomic molecules, then it's always going to be London forces. If you have anything that's pure hydrocarbons, then automatically it's going to be London forces. And if you have any noble gases, automatically those are going to be London forces. So for pure hydrocarbons, they contain nothing but hydrogen that I'm underlining and carbons, hence the term hydrocarbons. They just cut off the part of the suffix called gen, like hydrogen. They got lazy. So for example, if I have something that's written like this, C18H108, automatically, if it only contains carbon and hydrogen, then it's going to be London forces. Why is that? Because no matter how big and ugly the molecule is, it turns out all of the dipoles cancel out. So they have no overall dipoles, so therefore it's going to be London forces generating those temporary dipoles. And then noble gases, well, they don't like to bond with anything to begin with. So automatically they're going to be neutral and have no overall dipole. Therefore, radiant energy will cause the induced instantaneous dipole effect. So some helpful hints for you to automatically be able to identify these without having to draw the structures. Now I'm going to go backwards to the difficult one. And this is hydrogen bonding. You should be spending a lot of time understanding this concept. This is very important. If you take any other type of science classes, they refer to hydrogen bonding a lot, and if you understand the rules of identifying it, then you'll be in good shape. So first off, hydrogen bonds are super dipoles. The best example of hydrogen bonding is water. So first off, each one of these does have an overall dipole that goes this direction. Notice this is why the shape is so important, because they don't cancel out. They go in this. They go in these directions. More importantly, molecules that hydrogen bond, they have a nitrogen, oxygen, or fluorine. These atoms are very electronegative. So they really pull on the electrons. Consequently, they create very strong partial negatives and partial positives. Now, hydrogen is pretty much the weakest electronegative, so when it's faced with the three strongest, then it almost severs the bond, but it still manages to hang on a bit. But the electrons are not around it, so it's a partial positive. So, but these really big partial positive and really big partial negatives. So that's why I said the word super dipole. Now, there are some key characteristics that all hydrogen bonding molecules have. There's always going to be a lone pair on a nitrogen, oxygen, or fluorine for one of the molecules. So I'm just going to label this molecule 1 and molecule 2. And you'll notice on the first molecule, and I'll go ahead and I'll use my highlighter, there is a lone pair on the oxygen. The second molecule, or the other molecule, is going to have a hydrogen that is directly, covalently bonded to a nitrogen, oxygen, or fluorine. And again, this is for molecule 2 or for the other molecule. So I'm just going to go ahead and highlight this as well. So there is my hydrogen, and it's directly attached to an oxygen, for example. Now, you can have the lone pair on a nitrogen or lone pair on a fluorine, and then a hydrogen on a nitrogen and a hydrogen on a fluorine. So there are some options. So, but you do need these two criteria for it to be a hydrogen bonding, along with it having an overall dipole. So let's go ahead and show you another example. Down below, I could have something that looks like this right here. This is called methanol. Here's the overall structure. This is considered hydrogen bonding. And on the first molecule, you'll have a lone pair on the oxygen, which completes criteria number 1. And then on the second one, you'll have a hydrogen on there. And so therefore, you will have hydrogen bonding. And matter of fact, it's such a strong hydrogen bond that you can actually trace the bond. And we use dashes sometimes. It's what we call directional. Let's show you some other examples. I could have something like this, where it's ammonia. First molecule. Uh-oh. Let's do it again. So this is called ammonia, or also known as nitrogen trihydride. Notice how I'm always including the lone pairs, so it requires that you draw these Lewis structures properly, and you know how to do those. They both have an overall dipole that goes up here. And then the first molecule has a lone pair on a nitrogen. The second molecule has a hydrogen directly attached to a nitrogen, and this is considered hydrogen bond. Let's do another one. This is called dimethyl ether. It's great for cleaning car engines. So rather than draw out each of the covalent bonds, I just kind of summarize them together. But it has an overall dipole going up here, because oxygen is more electronegative than carbon. And then here's another one that's right here. The first molecule has a lone pair on an oxygen, but the second molecule has no hydrogen on the oxygen. Now keep in mind, it needs to be directly covalently bonded. If the hydrogen is on another atom, then it doesn't count. So the most that this could be is going to be dipole-dipole. Let's do another one. Here's hydrogen chloride. I drew 2 molecules. Because it does have an overall dipole, unfortunately, it's not one of the big 3. There is no nitrogen, oxygen, or fluorine present for the hydrogens to be bonded with, so the most that this could be is dipole-dipole. So here is water molecules showing the lone pair bonding to the hydrogen of another water molecule. Make sure you know these steps. Now, we're going to go ahead and first off, you don't have to memorize those specific examples, although I could test you on these, just FYI. But now we're going to get into something a little bit more challenging. We have something called pure substances, and it's the same molecules. And then we have mixtures. And those are going to be 2 different molecules. So for example, I could have a pure substance of what I just talked to you about, dimethyl ether. And if I do, if it's a pure substance, then I have to draw the same molecule twice as I do these hydrogen bond tests to see if it is a hydrogen bond or dipole-dipole. In which case, we figured out that this was dipole-dipole. Now, if I have a mixture, then things get more complicated. So let's say I have a mixture of dimethyl ether and hydrochloric acid, or hydrogen chloride. If I do that, then I have to come up with 2 intermolecular forces for each. So in this case, so I assess them separately. So the one on the left is going to be dipole-dipole, which we already figured out. And then the one on the right is going to be dipole-dipole. So that's considered a mixture. And we can actually extend this and go by the like dissolves like rule. Dipole-dipole, dipole-dipole, that's both polar and polar, and they'd actually mix together. Now, when it comes to hydrogen bonding, there is a third scenario. And this is where you have two different molecules, and one of them is water. One of them is water. So for example, I could have a mixture of water and this substance called dimethyl ether. It turns out that when you have a mixture, it is possible, going by the rules that we learned earlier, to have hydrogen bonding between the molecules. So I'm just going to go ahead and use my highlighter right there. The first molecule, for example, we look for an oxygen on a nitrogen, oxygen, or fluorine. There's a lone pair on a nitrogen, oxygen, or fluorine for the first molecule. The second molecule needs to have a hydrogen directly covalently bonded to a nitrogen, oxygen, or fluorine. There it is right there. So therefore, it's possible for there to be hydrogen bonding between molecules. So you'll notice the difference between the pure substance and the mixture with water. As a pure substance, it was dipole-dipole for that molecule. Over here on the right-hand side, when you're dealing with a mixture, unless it was water, then this dimethyl ether is still dipole-dipole. However, when it's water that's present, then going by the rules where one molecule has to have a lone pair on a NO or F, and the other molecule has to have an H on an NO or F, it's possible to have intermolecule hydrogen bonding. So this would be considered a hydrogen bonding. Ooh, that's as tricky as it gets for this stuff, though. So these right here are all examples of mixtures. Here's hydrogen fluoride and water, and then there can be hydrogen bonding in between. Here's ammonia and water. So there's a hydrogen on a NORF. There's a lone pair on an NORF, and therefore it's hydrogen bonding. Hydrogen bonding and hydrogen bonding. These examples right here, the molecules could be hydrogen bonding as a pure substance or a mixture. And then some molecules can have that extra hydrogen bonding as a mixture. I know that's deep. So you need to master each of these 4 intermolecular forces. You'll also hear me use the term dominant intermolecular force, because it's actually possible to have multiple intermolecular forces in the same molecule. It's as if they're competing against each other, and there will usually be a clear winner. So for example, this right here is methanol. It's a byproduct of distillation for alcohol. It's what makes moonshine so bad, because with methanol it makes you go blind and kills you. I digress. But on the right-hand side, we have the hydrogen bonding that can occur. On the left-hand side, we have London forces that can occur. Now, hydrogen bonding is a much stronger force than London, so therefore, hydrogen bonding is considered the dominant intermolecular force. Now, I'm not going to be putting you in a position for this class to label all possible intermolecular forces within a molecule. I won't do that. It'll just be one clear winner, and we'll just say that's the dominant intermolecular force. So make sure to know those. Make sure to go through all these concepts that you see here. And let's go ahead and pause for a second and go straight to the outline before we start applying this. Here's my outline. And we've talked about the concepts for all of these. And now let's go straight to the flowchart. This flowchart right here will allow you to assess whether each molecule is ionic, hydrogen bond, dipole-dipole, or London, as you see in this summary page right here. So if you get in the habit of following this flowchart and you master this flowchart, then you'll be able to instantly figure out the dominant intermolecular force for each molecule. Now, you're not allowed to have notes on a quiz or exam, but by mastering this, practicing it over and over, then you won't need it. So the first thing we do is are we dealing with a pure substance molecule or a mixture? And I will let you know If it says something like mixed in water, then it's a mixture. If it says pure substance, then it's only the same molecules. So if you're dealing with a pure substance, then you just have to figure out what the intermolecular force is by drawing the same molecule twice. So for example, I could give you something where it's a pure substance of HCl, in which case when you're assessing its intermolecular forces, you can just go ahead and draw two of them if you wanted to. Mixture, I could say something like HCl mixed in water, in which case you would draw one of each of the molecules. Now, usually, as mentioned earlier, if it's a pure substance, then you just name the intermolecular force for this one, and it happens to be dipole-dipole. On the other side, if it's a mixture, then you have to assess them individually. So in this case, the one on the left, hydrogen chloride, is dipole-dipole. The one on the right is hydrogen bonding. And then there's those special scenarios where you could have a candidate molecule such as nitrogen trifluoride, which would normally be dipole-dipole as a pure substance because it has no hydrogen present. However, when it's mixed with water, then both of these would be considered hydrogen bonding, because the lone pair on the nitrogen would hydrogen bond with the hydrogen on the oxygen. But I'm jumping ahead. So let's go to the next step. So after you figure out whether you're dealing with a pure substance or mixture, you take a look at the actual molecules. Is there a metal or polyatomic ion present? So for example, if I were to give you something like potassium fluoride, the minute you see a metal present, it's going to be ionic. And because it's above the cutoff line, right here, it's also classified as overall polar. So potassium sulfate, copper cyanide, those are all examples of molecules exhibiting ionic forces. Let's go to the next one. Let's say that you have a molecule that looks like this, F2. Let me just go ahead and erase all of this. I have a molecule like this, F2. So there is no metal or polyatomic ion, so go to step 3. And then the step says, is there a pure hydrocarbon, diatomic molecule that's the same atoms, or noble gas? In this case, this is a diatomic molecule, and it has the same atoms, so automatically it's going to be London forces. I don't have to draw out anything. So here are various examples of these. Those are all homodiatomic because of the same atoms, and then I have noble gases there, and I also have pure hydrocarbons, molecules that only have carbon and hydrogen. So that's pretty straightforward. So let's say I have a molecule that looks like this. Obviously, it doesn't meet the requirements for step 3, so you go straight to step 4. Is there a molecule with an overall dipole? So let's say I had a molecule that looked like this. I'd have to go ahead and make sure I drew out the Lewis structure. Obviously, I exceeded the octet with all those extra electrons. Awkward. Let's go ahead and throw away some of those. There we go. I have to figure out, as a pure substance, if this is an overall dipole, in which case there is. And if I were to draw two molecules, as you should, then it looks like this would be a dipole-dipole. But in this step, they want you to figure out, is there an overall dipole? So yes, there's an overall dipole for that HCl. If there's an overall dipole for that HCl, then you have to go to step 5. If there is no overall dipole, then it's automatically London forces. So if I had a molecule like this, HCl, then yes, there's an overall dipole, so I have to go to step 5. If I had a molecule that looked like this, oops, that's pure hydrocarbon. That's too easy. Let's do carbon tetrachloride. Chlorine is more electronegative than carbon. I put in the dipoles, and then they all cancel out, so there is no overall dipole. Therefore, that molecule is going to be London forces. Now I gave you some examples of molecules that have no overall dipole on the left-hand side and ones that do have an overall dipole on the right-hand side. But once we figure out it has an overall dipole, we then have to go ahead and figure out, is it dipole-dipole or is it hydrogen bonding? Before we do that though, you really need to be able to draw the Lewis structure. You also need to be able to draw its overall shape properly based on the rules that we learned in ionic molecular compound part 2 slides. So ionic molecular compound part 2 slides. And figure out, based on its shape, does it truly cancel out. So for example, that dimethyl ether that I keep talking about, it has a bent shape. So therefore, the dipoles don't cancel each other out like they do with carbon dioxide, and it has an overall dipole. So you really have to be comfortable sketching these out. Now, if our target molecule we're looking at has been classified with an overall dipole, and it's a pure substance, you're going to sketch 2 molecules. So let's go through the steps on this, even though I actually already did, but I'll do it again. And then you need to go ahead and go to 6 and assess whether it's hydrogen bonding or dipole-dipole. So if it's a pure substance, then you automatically, more arbitrarily, label one as number 1, number 2. Does the first molecule has a lone pair on a nitrogen, oxygen, or fluorine? So yes, the first molecule has a lone pair, but it's not on a nitrogen, oxygen, or fluorine. So automatically, the most that this could be is dipole-dipole. Now let's say I had a mixture, and I have hydrogen chloride mixed with water. Well, then I'd have to go ahead and draw duplicate molecules to figure out the intermolecular force for each of them. So with water, that's going to be hydrogen bonding. Hydrogen chloride, this is going to be dipole-dipole. So you always want to go through these steps. So now we have a third scenario. Let's say hypothetically I have a mixture, only it's mixed with water, just like the one I just did. And we also have to take into account the interaction between those water molecules. So I'm just going to go ahead and do the same one that I did before. By itself, it would be dipole-dipole. Here is the water. by itself, it's going to be hydrogen bonding. But now we need to go ahead and take into account if there is any potential intermolecular force hydrogen bonding that's occurring between the two different molecules. Let me say that again. We want to see if there's any intermolecular force hydrogen bonding between the two different molecules. So if we look to the left, there is no nitrogen, oxygen, or fluorine, so automatically it's no longer a candidate for hydrogen bonding, and it maintains its dipole-dipole. Let's do another one. I could have a mixture of water with let's see, OCl2 with H2O. So I draw both of the molecules, figure out what the intermolecular force is, assess them individually. So I draw two water molecules, and I can figure out that that's going to be hydrogen bonding. I draw two molecules, and I figure out that that is going to be overall dipole-dipole. But because we're dealing with water, now we need to go ahead and assess, is there any intermolecular hydrogen bonding between the two different molecules? So I'll just arbitrarily choose that this is candidate 1, this is candidate 2, and then I figure out, is the first molecule have a nitrogen, oxygen, or fluorine with a lone pair? And it does. It does. There's a lone pair on the oxygen. And I go to the next one. Does the second molecule have a hydrogen that's directly covalently bonded to an oxygen? It does. So it turns out the oxygen dichloride is going to be upgraded to hydrogen bonding when it's mixed with water. So now both of those are going to be hydrogen bonding, and then there'll be that due to the intermolecular hydrogen bonding between the oxygen dichloride and the water. So I've given you multiple examples down here as a pure substance. If A and B are yes, it's going to be hydrogen bonding. So here are examples of that as a pure substance. And then mixed with water. And it turns out for these examples, when they're mixed specifically with water, there's that intermolecular hydrogen bonding that occurs between the two different molecules. On the right-hand side, if one of these assessments is not completed, then it's automatically going to be dipole-dipole. And here are examples of molecules that don't complete the assessment for proper dipole-dipole. So I put two molecules here for each as a pure substance, dipole-dipole, pure substance, dipole-dipole. I like this one right here. A lot of people, when they do that one right there as a pure substance, they think that this is going to be hydrogen bonding, and it can't be. Just to demonstrate this, here's number 1, here's number 2. First molecule, they both have overall dipoles, FYI. First molecule does have a lone pair, but the second molecule has no hydrogen directly bonded to it. It's attached to another part of the molecule, but there is no hydrogen directly bonded to fluoride. So the most that this could be is dipole-dipole. And then here's mixtures that occur. And then this would be dipole-dipole, dipole-dipole. You have to assess them individually, what each of the intermolecular forces are. With water, you have to do that third intermolecular hydrogen bond assessment. But it turns out this hydrogen chloride cannot be hydrogen bonding because chloride is not one of the big three, nitrogen, oxygen, or fluorine. So you want to practice these this flow chart. The first 4 steps are pretty easy, and then the last 2 steps are very challenging that you have to practice over and over and over. But you can get this down, and you need to for future science courses that rely on solution chemistry. Alright, so let's go ahead and start going into examples. Name the intermolecular force and whether considered polar or nonpolar. So this is ammonia. This is going to be hydrogen bond, and that's going to be polar. CH4, this is going to be London force, and that's going to be nonpolar. Helium is London force, that's nonpolar. Ammonium hydroxide, because of the polyatomic ion, it's going to be ionic and polar. Hydrogen sulfide, if I drew it out, it's going to be dipole-dipole, but it because it doesn't possess the big 3 atoms, nitrogen, oxygen, or fluorine, it can't be hydrogen bonding. So it's dipole-dipole and polar. Carbon monoxide, that's going to be polar. You had to memorize that molecule along with hydrogen cyanide and oxygen, and that's from the ionic molecular compounds part 2. And so carbon monoxide, that's going to be dipole-dipole. Hydrogen cyanide is going to be dipole-dipole. Careful, even though it has a hydrogen present, it's not directly on the nitrogen. So the most it can be is dipole-dipole. Oxygen is going to be London force. I'll go and I'll speed up now. And then pure hydrocarbon, that's called ethane. That's going to be London force. London force. 1-chloromethane, that's going to be dipole-dipole. That's going to be hydrogen bonding. Water, shocker, I'll let you figure that one out. Argon, that's going to be noble gas, so it's going to be London. Hydrogen bonding, London force, ionic, dipole-dipole, hydrogen bonding. It should be a lower, small 3, but oh well. That's going to be dipole-dipole, dipole-dipole, and then this right here is going to be hydrogen bonding. So you should be able to sketch the structures and come up with these its overall shape, apply the overall dipole rule, and then apply the extra rules, and then figure out whether it's going to be polar or nonpolar. So practice, 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 practice. Now all these examples right here, even though I didn't state it, these are all examples for pure substance. Let's go and jump right into mixtures. So this stuff, a lot of the slides are from the previous discussion on solutions. So even the same slides should be very similar to what we've already talked about. And so salt is a lesser amount, water is a greater amount, so solute, solvent. It's going to create a solution. Here we have water and copper sulfate, and that's a solution. The solute spread out, and now we know that water is hydrogen bonding, that's polar, copper sulfate's ionic, and then like dissolves like, so they're soluble. And then the lesser amount is always going to be the solute. The greater the amount will always be the solvent. So it's a numbers game. So there's 2 grams of sugar and 100 mils of water, so therefore water is going to be the solvent, sugar is going to be the solute. and all together it's called a solution. Assuming that it mixes perfectly for a solution, but we just go by the term solution. Alright, so let's go ahead and move on. We've already talked about the dissolving process, but let's bring it up again. When you have a solid sodium chloride, the water molecule likes to go ahead and pick apart the individual ions and surround it in what's called a solvent cage. And it's due to opposite charge attraction. So for example, if I have a lithium with a positive charge, let's draw it again, lithium with a positive charge, and water molecules have that super powerful dipole where the oxygen head is a partial negative, then opposite charges attract. And it suspends the lithium ions in that solvent cage due to opposite charge attraction of its oxygen super powerful dipole negative charged head. That's a lot of words. It's like me saying Mighty Morphin Power Rangers. Alright, let's move on. If we're dealing with a chloride, then that's going to be completely backwards, where the hydrogens are going to be facing from behind. Now, applying our intermolecular force rules in determining whether something dissolves. Water is polar. Let's figure out what each of these are. That's ionic, therefore that's polar. Gasoline's nonpolar. Iodine is going to be London forces, and that's going to be nonpolar. And hydrogen chloride, it's hard to tell, but it's at number 4 is hydrogen chloride. That's going to be dipole-dipole, and that's polar. So the first one is going to dissolve. That's a yes. Gasoline, that's going to be a no. Iodine is going to be a no. And then hydrochloride, that's going to be a yes, because like dissolves like. So going through these really quick. London force, that's going to be, excuse me, that molecule right there, carbon tetrahydride, that's going to be London force. So that's going to be nonpolar. This is polar, and it's soluble. Ionic forces is polar, water is polar, soluble. Methanol, hydrogen bonding, so it's going to be polar, water is polar, soluble. NH3, that's polar because of hydrogen bonding. Pure hydrocarbon, that's nonpolar, so that's going to be insoluble. Water and chloride, polar for chlorine gas is, let me say it again. Water is polar, chlorine gas is nonpolar, so that's going to be insoluble. Methane and ethane, they're both pure hydrocarbons, so they're both nonpolar. That's going to be soluble, because like dissolves like. Polar, nonpolar, that's going to be insoluble. And the bottom one, NF3 and H2O, polar, polar, that's going to be soluble. So that's what you'll be expected to do on a future quiz or exam. Let's go ahead and go into electrolytes. Now, there are some molecules or particles, I'll use the term particles, such as NaCl, and when you put them inside water, they separate into ions. Now, if we were to sit there and connect up a battery, completing the circuit with a light bulb. There's my light bulb in the upper left-hand corner. Electricity could be conducted through the ions to complete the circuit. So let me go ahead and draw that one again. There are the wires going into the solution. There's the sodium and chloride ions, and I'll use my yellow marker. Electricity is conducted through the sodium chloride solution, and that's because they pass through the ions. So this is where we get another name for dissolved ions. We call them electrolytes because ions can conduct electricity, ergo electrolytes. And a lot of fitness companies like to use that term in their drinks. So this contains a ton of electrolytes. Well, that's actually referring to the salts inside the water, as opposed to saying this contains a ton of salts. Electrolyte sounds cooler. But bottom line is, if you ever have an ionic compound and it completely 100% dissociates into ions, then we have a maximum conductivity. It'll conduct electricity, and therefore you'll have a really strong current going through. So therefore it's a strong electrolyte. On the other hand, there are some molecules that don't turn into ions. So sugar molecules, there is 0% conversion into ions. So therefore it's a non-electrolyte. So right here in this example, everything stays as a sugar. It's neutral, so therefore electricity cannot be conducted through it. And as proof, you don't see the light bulb going off. Now, there are these in-between molecules called weak electrolytes, and they really can't make up their mind. So for example, the best example is hydrogen fluoride. So if I have hydrogen fluoride, then you're going to have a partial percentage of molecules dissociating into ions. Furthermore, as soon as they turn into ions, they may change their mind and turn back into the neutral molecule again. As a result, if you were to sit there and look at the species inside a solution of water, some of the molecules are in ion form. Other molecules are in their neutral form. Therefore, weak electrolytes conduct electricity weakly. So, hydrogen fluoride is a weak electrolyte. So here's another example, and it shows some of them as ions, other ones have not. So you're responsible for those terms, strong, weak, and non-electrolytes. If I give you any information about the conduction of electricity, you should also be able to infer whether it's a strong, weak, or non-electrolyte. So these slides talk about strong and weak. Again, for weak electrolytes, they may change their mind. So as soon as they form their ions, they may go back and form the original neutral molecule. Here's non-electrolytes. Even though they dissolve, it's not into ions, so they don't conduct electricity. So here's an animation. That is solid sodium chloride on a atomic perspective. Because it's not an ion, it can't conduct electricity. So there's the wires. If you take a look at my my mouse icon, arrow icon, the wires are put into the solid sodium chloride, but it can't conduct electricity and complete the circuit, so the light bulb doesn't go on. Now if we mix it up with water, then you know the sodium chloride is going to be turning into sodium and chloride ions. So there's the water, there's the sodium chloride. They're broken up into ions. and ions conduct electricity. So they put the sodium chloride in there, and then voila, the light goes on. So it's a strong electrolyte. Now they went ahead and they put sugar in there, and even though it dissolves, it doesn't form ions, so that's a non-electrolyte. Now if I put a weak electrolyte in there, then it would just shine weakly. Okay, so now we're going to get into a different topic. We're going to get into solubility. So these next couple topics are actually really easy. Solubility is the maximum amount of solute that dissolves in a solvent. Using my son as an example, I once gave him a bowl of cereal, and I allowed him to go ahead and put some sugar inside the cereal. And he thought it was cool that the sugar would go ahead and eventually dissolve in the bowl of milk. And then I'm erasing that portion because that's the sugar dissolving. He then found out, amazingly, that if you put too much sugar inside a bowl of milk, it stops dissolving. And it just sits out. So solubility is the maximum amount of solute that dissolves in a specific amount of solvent. No, I did not allow him to eat that bowl of cereal. I drank it all myself. So scientists have spent hours and hours measuring out how much solute can dissolve in 100 grams of solvent. In general, if you are if you do not put enough solute in, then we say it's unsaturated. So everything dissolves if it's unsaturated. You can put in more solute. On the other hand, if you're past the solubility limit, then we say it's saturated. So this is what it kind of looked like with my son and cereal, only that would be sugar. So know the terms unsaturated and saturated. And based on these solubilities, you can immediately figure out whether a solution is going to be saturated or unsaturated. So for example, if I put in 80 or more, it's going to be saturated. Less than 80, it's going to be unsaturated. So for part A, if I only put in 60 grams, then that's going to be unsaturated. So this is a ratio. And we can go ahead and apply the ratio for the next one. So if I double this, and this is 160 over 200. If I have more than 160, then it's going to be saturated. So part B is going to be saturated. Let's move on. So in this part, we just want you to know the trends. We don't go into details why, just that it happens. So as far as solubility goes, solubility can be affected by temperature, and therefore the solubility of most solids increases as temperature increases. So you should make a little note that for solids, increasing the temperature means you increase the solubility for the solid. On the other hand, if we're dealing with a gas, then gas solubility decreases as temperature increases. So on the other side, I'll just say gases, and then memorize this trend. As temperature increases, gas solubility for gases decreases. You don't have to memorize all these numbers here. I just want you to memorize the trends. So why would a bottle of carbonated drink possibly explode when it's left out in the hot sun? Well, this is a gas formula. So as the temperature increases, the solubility decreases. So here's my soda. There's my carbon dioxide. And when we blast it with the sun, it gets hot. Well, all that carbon dioxide, because it's not dissolved in liquid, is going to go ahead and go into the empty space, into the air inside the soda can. And eventually there will be so much carbon dioxide that builds up in that empty space that it's going to cause the soda can to burst. Why do fish die in warm water? So there's my fishies. It needs oxygen. So again, if the water is too warm, then all of the oxygen leaves the liquid because it's not as soluble anymore, and therefore the fish die. Now, Henry's law talks about gas solubility, only instead of looking at temperature, we're looking at an external pressure. So let's just go ahead and give you a generic example. Here's a liquid in an open beaker. There's my carbon dioxide. And then outside we have atmospheric pressure pushing down. And Henry's law states for a gas dealing with an atmospheric pressure that as you increase in atmospheric pressure, you increase in solubility. And that's because as the carbon dioxide starts to leave, the gas from the atmosphere pushes the carbon dioxide back in. So just as it starts to come out, it pushes it back in. So if you go to a soda can, if it's closed, then as the gas particles escape, they're bounced back and pushed back in because it's a closed container. On the other hand, if you open up the soda can, you have a lot lower pressure than the closed soda can. And even though you have atmospheric pressure pushing down, it's a lot lower, so solubility drastically decreases for the carbon dioxide and it escapes. What I want you to know, I just want you to know this relationship. As the atmospheric pressure increases, the solubility increases. So know those relationships, and we are done with intermolecular forces and solutions part 1. Study, 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 and master these concepts.